Okay, first let me thank IPAM, the organizers, and the chair Anatol for this opportunity. Given that mine is the first talk, I'm going to provide a little bit of background, which I hope will be useful for especially the younger people in the audience. Right? So the title of my talk is rather broad. So I'm going to show a few examples of machine learning applications in material science that we have undertaken. And I was actually very pleased to see this as the theme of the theme image of this workshop. This is actually a picture from our first machine learning applications in material science paper. Okay, so as I said, the plan for today will be a little bit of background on machine learning, not necessarily applications in material science first, and then I'll go on to some examples of how we and some others in the community have used machine learning within material science. Right? So that's the plan. Right? So let me start off by this question. What is machine learning? Well, let's provide a context when machine learning is typically used. Right? A pattern exists. We have a feeling that a pattern exists, but we cannot exactly pin it down mathematically at the outset. Right? But we have plenty of data. We have a lot of data. We have a lot of examples, and so we would like to use that to nail down what that pattern is. Right? The concept is, of course, we want to build a predictive model based on the data that's available, based purely on the past experience and past data, rather than explicitly solving scientific equations. Right? So that's kind of the approach that the machine learning community, broadly speaking, has applied. And one important thing that comes up is this concept of adaptiveness. Right? So the prediction model, the prediction scheme, has to evolve as more and more data accumulates. Right? And the prediction power has to increase in quality as more and more data accumulates. So this adaptive feature has to be a part of the scheme for it to be called as machine learning. And I'll touch upon that at the very end of my talk as well. This is something Alan Turing kind of hypothesized in the early days. Right? Okay, so an example. I'm going to choose an example from something like Netflix. Right? How does Netflix give recommendations, make predictions based on what you as a user would want to view? Which movie do you want to watch? Right? So we're all boiled down, reduced to numbers. A viewer, based on his or her viewing preference, is actually broken down into a string of numbers, a vector. Right? Does the viewer like comedy? What is the numerical factor that represents comedy? The comedy liking of the viewer. Does the viewer like action movies, etc., etc.? Does the viewer like Tom Cruise? Right? So based on that, you have a numerical vector, and then of course every movie has a corresponding numerical vector. Is it a comedy movie? What is the comedy content? What is the action content? Does Tom Cruise act in the movie? Right? So two vectors, two numerical vectors, and of course these two are matched. You can match them in many ways. Of course, you could conceive a dot product of the two. If the dot product is very low, then the match is poor. The dot product is high, match is high. Or you could also look at distances, right? Euclidean norms, for example, between these two vectors, and based on that, one can come up with a recommendation based on past data. Right? By the way, this example is from this very nice, very readable monograph, very nice book. And here is another example based on how a bank may decide to give credit to a customer, to a client. Right? So applicant applies for loan to the bank. His age is so much. Gender, of course, is male in this particular case. Salary, years in residence, etc., etc. Right? So a number of metrics, descriptors that decide whether this guy is going to get his loan or not. Right? So now this is a numerical vector, and if there is a lot of past information, in the past, humans actually made the decision on whether to give a loan or not. So if a lot of past information is available, and now if you have a huge volume of people applying for loans, maybe this past this vast amount of past data can be used to make judgments in the future in an automated manner using a machine, right? So the question, of course, for the machine is to whether the credit should be approved or not, right? Whether this works out very well or not is a separate topic. I'm not going to touch that, right? So now let's get down a little bit to the nuts and bolts. Let's say we call something as the input, input vector or input, which is X, could be the customer application, that vector. Output is Y, whether this is a good or a bad customer, that's the decision one has to make, right? And there is plenty of past data available, historical records on X, Xi, Yi. And of course, the machine has to come up with a hypothesis based on this past data, some kind of a relationship, some kind of a mapping between X and Y, right? So that's what I'm calling as a hypothesis. This hypothesis is to be determined, refined, and if it works out well, it can be used in the future, right? And of course, I'm not going to go into the nuts and bolts such as training, how to choose a training set, how to do cross-validation, things of that nature. But the common practice is that, well, you have a bunch of data, you break that up into a training set, and the remainder is put in the test set. The model is actually trained on the training set, and then assessments are made whether the model is right or not based on how it predicts stuff for the test set, right? So that's kind of how the idea works, right? When do we use machine learning? When is it generally used, right? I kind of break it up into three general situations. Say a situation has no fundamental laws. At least we have no idea whether there is a fundamental law underlying a certain situation or not, or maybe there is just no fundamental law. When fundamental laws underlying a particular situation or process does not exist, right? Classic example of this situation occur in social sciences, right? Population dynamics, etc., right? There are a lot of situations where it's hard to figure out whether there is a law or not, but you use data to make predictions. Right? The second scenario is when fundamental laws exist, but they are just too complicated. Example could be weather predictions, right? Laws exist, the equations, we know what equations we need to solve, but the equations are fairly complex, at least today, for us to brute force completely solve them. Third example, third situation is when we have a lot of data and we are actually looking for rules and correlations. Example could be within material science, could be Hume-Rothery rules for solid solution, solid solubility. It could be the Hall-Petch equation. If you're familiar with mechanical behavior of materials, how strong is a material is actually captured by this beautiful equation called the Hall-Petch equation, which relates the strength of a material to the grain size, or if it's a polycrystalline metal, for example, right? So again, this is not a fundamental law, but it captures certain hidden correlations. Right? So within material science, I don't think we need to worry about the first one that much. We are really in the second and third bullet arena. Right? Okay, so now I'm going to get into material science, right? So how has things happened in the last several years, let us say, within material science? How has machine learning been used, right? So the traditional approach is we have a material, we either use computations or experiments to determine relevant properties of that material. Right? We go through this process laboriously and carefully over and over again, and in the process we accumulate a fair amount of data. Right? The question is whether we can use that knowledge to bypass this pathway and actually go through this pathway. Right? So if we can reduce materials to fingerprints, descriptors, attributes, etc., perhaps we can establish a mapping directly between those descriptors and the property based on this pathway, right? Based on the data that we have accumulated using the traditional pathway. If this is possible, then it can work to our advantage. We can go from material to property much faster. Right? So that's the idea. So I would like to bring to your attention a couple of papers, one written by us recently, where we kind of attempt to review what has happened in the last 3 to 5 years, which I should say this paper is already somewhat outdated because the field is moving so fast. So many people are doing work in this area right now. This is already somewhat outdated. There's another review here by Chris Wolverton, which actually focuses a lot on fingerprints. What are the different ways of fingerprinting materials, at least within the atomistic simulations. Okay, so what I'm going to do is I'm going to say a few things about the fingerprint. How do we fingerprint these materials, right? Fingerprint is key. In this whole process of going from material to fingerprint to property, this whole thing, of course, could be called as machine learning, but the critical step in that whole procedure, and I think we all recognize that, the fingerprint, defining the fingerprint and choosing the descriptors appropriately is perhaps the most critical step in the whole thing. Right? Let me say a few words about that. As I said earlier, the fingerprint is nothing but a numerical representation of the material. In the case of the banking example, it's a numerical representation of the client. In the case of materials, it's a numerical representation of the material. We'll define it properly soon. The community has realized that, of course, this fingerprint has to be defined based on the application and based on domain knowledge. Right? We need to know the class of materials well. We need to know the problem we are trying to solve very well, and we need to know what sort of properties we are trying to arrive at. Right? So based on that knowledge, the fingerprint has to be properly defined. It also depends on the application. The fingerprint has to be intuitive, and it has to be inexpensive to compute, because if it is very expensive to compute, it defeats the whole purpose of using machine learning. It should be far less expensive to compute the fingerprint than doing, let's say, a quantum mechanics-based calculation. Another very important thing is that the fingerprint should be invariant to certain transformations. If you just rotate or move a material, the fingerprint should not change, because the material is the same thing. So the fingerprint should be invariant to transformations of the material, such as translation, rotation, permutations of like elements, and so forth. Right? And finally, this is something I just want to underline. The fingerprint can be macroscopic, mesoscopic, or microscopic. It completely depends on the problem that we are trying to solve. Right? At what level should the fingerprint be is going to depend totally on the application. So what I'm going to do now is I'm going to actually provide one example for each of these three: macroscopic, mesoscopic, and microscopic. That's what I'm going to do. Those are three examples I'm going to show. Okay, first example one is a macroscopic fingerprint. So what I'm going to talk about here is our effort. I'm going to summarize our effort to understand how a complex property of a material, in this particular case, the breakdown strength, the electrical breakdown field of a material, can actually be learned. How it is controlled by basic material attribute, how that can be learned is what I'm going to summarize. Right? Now, let me give a little bit of a preamble here. When I say electrical breakdown, here is what I mean. You take an insulator, you apply an electric field to it. You keep cranking up the electric field. At some point, this insulator is going to break down, meaning it's going to leak and start conducting. Right? So this will be a irreversible process of conversion of a insulator to like something like a metal. Right? So when the field at which that happens is what we call as breakdown field. This breakdown field is fairly complex. It's but under certain special situations, it can be computed. The situation is intrinsic breakdown. If you take a perfect defect-free material and you subject it to electric field, there's a critical field when it breaks down. There's an avalanche of electrons that go through it. Right? It's controlled by electron-phonon interactions. Now, I'm actually not going to be talking about the details of how we compute the intrinsic breakdown field, because that's a different talk. What I'm going to do is I'm going to just show you the results of how we have computed the intrinsic breakdown field for a benchmark set of insulators, and I'm going to show you how we have learned some correlations between the intrinsic breakdown field that has been computed and other key attributes of the material. So this is what I just said. Predicting the intrinsic electrical breakdown of an insulator from first principles is difficult, but it can be done. It is determined by the balance between energy gained by an electron from the electric field and energy lost to phonons. And the way and the methodology for that goes all the way back to the 1940s, to Froelich and von Hippel's work. So recently we have been able to implement that in quantum espresso, and we've been able to calculate the breakdown field. But the question I want to ask here is, can the breakdown field be estimated rapidly using a machine learning based model, right, rather than through expensive quantum mechanical calculation. So as I said, we are talking about intrinsic breakdown behavior, and that is actually totally dependent on the chemistry of the material, right? So what we did was we considered 82 binary octets drawn from the periodic table. Examples of binary octets are sodium chloride, lithium fluoride, gallium arsenide, zinc oxide, etc. Right? There are 82 of them that we can draw from the periodic table. And what we have done is we have computed the intrinsic breakdown field for those 82. And we have validated them against some experimental information that is available. For about a dozen or so of the binary octets, experimental information is available. So we've been able to validate our calculations against that. So I'm not going to show you all of that. I'm just going to show you the results, right? I don't know what happened there. So okay, so here is a periodic table I just showed. Here are the results. There are 82 binary octets listed over here, and what is plotted here, which you probably cannot see too well back there, is the computed intrinsic breakdown field for all of them, right? So you can see that there are some periodic patterns. That was the first signal to us that there may be some hidden correlations. Okay? What we wanted to do was to relate these computed values to easily accessible material properties. So this is our fingerprint. It's a macro level fingerprint, right? It's a fingerprint that is based on material properties. So this is a complex property. These are all well-defined properties, right? So what is there a relationship between the computed intrinsic breakdown field and some subset of those? That's the question we wanted to ask. Yes.
Is there an order to the horizontal axis on that plot?
There is no. Okay, let's see. Okay, let me go back. Is there an order? Actually, there is some kind of an order. So the elements, the compounds have been grouped based on their anions, right? So for example, so these are all lithium compounds: lithium fluoride, lithium chloride, lithium iodide, lithium bromide, lithium iodide, and then sodium fluoride, and so forth. So they have been ordered based on the anions. Yeah.
So
Yes.
It seems that you are using the periodic table order,
Yeah.
and then doing the anions
Mm-hmm.
on the periodic table. So in a way, it's a nested periodic table.
Yes. Yes. Right.
The
Right.
reason I said was because then it almost makes sense.
That there would be some trend.
That's
Correct. Absolutely. Yes. Right. But we don't rely on that trend when we try to establish a mapping between left and right. Yeah. Okay. So what we do is okay. This is a list of I believe eight properties, 8 macro level properties that we have selected. And what we now do is we want to establish a relationship between the computed breakdown field and these. So here is what we do. Okay. We create a bunch of prototype functions. Okay. And they are listed over here. Right. So let's take one of them. Let's take the band gap, right? Band gap x, when x can stand for any of these. So when it's x, we take band gap. That's reciprocal of the band gap, square of the band gap, and so forth. Right. So we have created 12 prototype functions based on just the band gap. And likewise, we create prototype functions based on each of these properties. So since you have 8 there and 12 there, you got 96 features. Right? So now we cross multiply the 96 features against each other. So we get 96 times 96 at 4,000 something compound features, and then we find triples. We take 96 times 96 times 96. That gives us 183,000 compound features. You add them all up, you get about 187,000 features. So now we call these as compound features. And by the way, this whole strategy is inspired by recent work from the Fritz Haber Institute, where they've done something very similar to understand the structure of binary octets. So anyway, so we have a fairly large number of compound features, and we now want to see if there is a linear relationship between our breakdown field and some subset of these features. So that's the idea. Right? So for that, we use LASSO. Again, I'm not going to go into the details. Least absolute shrinkage and selection operator is the technique that we use to go from 187,000 features, and we find a small subset that are linearly correlated with our breakdown field, and we come down to about 36 compound features. The 36 compound features are kind of listed over here. Not all of them, but a selection of them. And we use our human intuition, I guess, to select one of them. I mean, I'm just going to talk about just that because I like that because it's kind of simple, and I even am able to attribute some physical meaning to this kind of a relationship, right? Square root of the highest phonon frequency that the material experiences, displays, and times the square root of the band gap. Right? So now I'm going to show you how actually the correlation works. So this is the machine. So this is the formula. The breakdown field is related to the square root of the band gap times the phonon cutoff. And here is a plot of the actual DFT result versus this formula, machine learning. Right? The red spots that you see are the training set. The yellow stuff that you see, that's the test set. And you see there are some white symbols. They are compounds that were not in the training set. They were not among the 82. They are not binary octets. Right? So we wanted to just try it out on new compounds that were not part of our original data set. And as you can see, the correlation is not super accurate, but it is quite interesting that we can get things somewhat right over 3 orders of magnitude. So now that's exciting. So because we have now established somewhat of a relationship now between the breakdown field, intrinsic breakdown field, and some easily accessible properties which we can compute with no problem. Now I have to add a caveat though. This is a heuristic. This is not a law. Right? We cannot take it too seriously because there are other functions, other compound features that also correlate somewhat to the same extent. Right? So this can be used for screening and so forth, but this is not something that we want to take too seriously. We don't want to argue that the breakdown field is given by this formula. Now going forward, we have applied it to new cases. That the power of a heuristic is that you can actually apply it to new cases which you have not seen before.
Why are you saying one-dimensional? Why not really doing a linear combination of? I mean, you had several very good features.
Correct. Yes, we did that, and of course the agreement it tightens up. But then it becomes
It's still a simple formula.
It's a simple formula. Absolutely, we can do all 36. For example, contracted it to 36. What you're saying is that why not use all 36? Actually, we have done that.
At least the best 5.
The best, yeah, sure. We have actually done that, and it tightens it up even more, sure. But this is the simplest of them all. And that's why I'm showing that.
Excuse me, how do the
Yes.
36 differ? More by the functions or more by the primary features?
Both.
Some by the physics, right? Because they really probe different aspects of the physics.
Correct. So
That's why I felt actually combining them makes a lot of sense because.
sure. Actually, let's go back and let's look at this thing here. So Anatole, your question. Phonon cutoff, band gap. So in the first few features, the phonon cutoff and band gap persist, and I believe this is what Matthias is saying. If you take the first 5, for example, phonon cutoff and band gap keep showing up. As you go further down, you get the nearest neighbors and mean phonon frequency and other properties begin to emerge. But the top 5 are dominated by the phonon cutoff and the band gap.
Which probably is actually close to a law. That these are the, I mean, at least it makes sense that these things determine the breakdown.
Yes, sure. But then that particular formula, I cannot argue that specific formula is a law. Yeah. Okay, so let me show you this. We've gone further, right? So we now considered perovskites, ABX3 compounds, which occur in the perovskite crystal structure. We considered a couple of hundred of those, which are insulators, and which are stable in the perovskite structure. Not all ABX3 compounds are stable in the perovskite structure. Right? So we chose a couple of hundred of those, and for those, we use computed the band gap and the phonon cutoff, use the formula I showed earlier, and here is a plot of the phonon cutoff versus band gap for those 209 cases. Those are the red symbols. This dashed line that you see, the shaded region beneath the dashed line, that's the region that we actually believe our model to represent properly, because our data set of 82 binary octets have band gap and phonon cutoff in that shaded region. So if we are going outside of that, we are really going somewhat out of domain. Matthias.
Have you done a systematic investigation of the ability of these formulas to generalize beyond their original domain where they were trained? So we know that the
Yes, we are
interpolation models.
Yeah.
All of these.
We are working on that right now because we have a bigger data set, right? So yes, we are working on that. So right now we are just applying that formula, right? And then the interesting thing that we are finding with the perovskites is that these lines here are contours of constant breakdown field. So as you go to the top right, you're actually going to high breakdown field compounds. And if you look at these cases over here, they are all dominated by perovskites containing boron. We don't know exactly why. This is something we are working on. We are trying to figure out. So this scheme has allowed us to go from binary octets to other compounds, and they have helped us. They have raised flags on what could potentially be interesting. So now it's our job to go deeper and see what's going on with these boron-containing compounds. Yes.
Do you find the pure element boron has high breakdown field?
We have not considered pure boron actually, because, well, I guess we could. We have not, yeah. Because boron has a very complex unit cell, right? It's a pretty big unit cell. So it's going to be difficult for us to validate what our machine learning model is predicting. We are considering those cases where we can go back and do a DFT calculation to calculate the breakdown field, right? With the boron, pure boron, we may run into some difficulties because of the largeness of the unit cell, right? But that's a good point. Yes?
How many binary compounds did you have in a training set when you did the finishing calculations?
There were a total of 82 binary octets, out of which we chose 65 or so in the training set. Right?
Is that number too small? Could that be an issue?
We checked for convergence with respect to the training set size, right? After a point, it doesn't change, right? So I believe about 90% of our 82 compounds is what was put in the training set. And beyond that, it didn't really make that much of a difference. But if you are well below 90%, then of course it's unstable. Okay, so that's my first example. So I'm going to move on to my second example. So that was an example of macroscopic fingerprints. Now we're going to go to mesoscopic fingerprints, right? By the way, mesoscopic fingerprints have been used to a very large extent by the chem informatics community, drug design community for decades. Right? What they do is they choose their molecules or compounds and they represent them in terms of fragments, right? Building blocks, motifs, and so forth. Not exactly atoms or atomic position information is not put in, but groups of atoms are considered. Right? Okay, this is part of a much bigger project that we are currently involved in, where the goal is to design polymers with large dielectric constant and large band gap. Right? Good dielectric, good polymer dielectrics. That's what we are actually involved in, right? Designing. As part of that work, we had to explore a fairly large chemical space occupied by polymers. For example, let's consider this fragment. It's a repeat unit of an infinite 1D chain. Each of these blocks could be populated by one of these or other groups. If each of these blocks is populated by CH2, you get the most common polymer, polyethylene. Right? Now the question is, if you now populate each of these 4 blocks with any of these, you will get a huge number. You will go through a combinatorial explosion. Right? So what we wanted to do was to identify if we can reliably and quickly estimate the band gap and the dielectric constant of these polymers. That was the goal here. And the way we wanted to fingerprint these materials is by using fragments. Right? So a very, very rudimentary, easy way of fingerprinting this is by just keeping track of the number of CH2 units, number of CO units, number of NH units, etc., for a given polymer. That's basically keeping track of composition. Turns out that that doesn't work that well. Right? So next in the hierarchy would be keeping track of pairs, doubles. How many CH2 units? How many CH2 NH units? How many CH2 CO units are there in our polymer? That is that performs moderately well. What works really well for us is triples. Right? How many CH2 groups are in the polymer? How many CH2 NHCO groups, etc., etc. So we keep track of triples, right? So that's what I'm listing here. So that's what we have used to fingerprint our polymers. We have computed the band gap and the dielectric constant for few hundred of these polymers using density functional theory, and that's our data set. So since we have the properties now, and since we have a fingerprinting scheme now, the goal is to map the fingerprint and the property, for which we use kernel ridge regression. Right? So what you see in this picture over here is the fingerprint space, the feature space, right? And the red dots are compounds, polymers for which we know the answer already. So these are points in the fingerprint space, and this is a case for which we want to know what the band gap is or what the dielectric constant is, right? Now again, I'm not going to go through the math on this. I do want to point out that this paper written by people in this group has actually set the stage, set the tone for a number of other related activities. Right? So kernel ridge regression was used in this work, and that's the same scheme that we use in this particular polymer design, polymer discovery work. And I'm just going to show you the results. Right? So let's look at this plot. The electronic part of the dielectric constant, density functional theory predictions on this axis, and machine learning predictions on this y-axis. The red stuff, the purplish stuff is training set, and then the red stuff is test set. Right? And what you see in this inset over here is the error. Right? So the distribution of error, the error between the machine learning prediction and the DFT calculations versus the frequency of occurrence of that error. So you can see that this is the level of accuracy that we can achieve with this type of fingerprinting scheme for this class of compounds. This is for the rest of the contributions to the dielectric constant. This is for the band gap. Typically, we get errors. If you look at the 1 sigma distribution of errors, it's of the order of 7–8%. This is the sort of accuracy we can expect from these models. Now the thing is, well, we can create a model, we can make predictions, but the real impact is to make predictions for unknown cases. Right? And this is the case. This is what my collaborators, my synthesis experimental collaborators are interested in. My synthesis colleague comes to me and then asks and tells me, well, here is a polymer we can make in the lab. We can get started on it today. Can you tell me if it is worth making or not? So if I use density functional theory based computations, it will take me days to make a reasonable judgment, right? But with machine learning, with this prediction model, we can actually do it instantly. So we kind of distilled it down into a usable model, and it's actually an app that's available in our website, right? So the name of the location of this website, the app is kazana.uconn.edu, and here is how it works. So here is a drop-down list of menu items. So Greg Sotzing, my experimental collaborator, can actually go in here and say, okay, I want NH here, CO, NH, C6H4, and then he hits predict properties, and then boom, we can, so that's the polymer corresponding to NH, CO, NH, C6H4, right? And we have 2 machine learning models to make this prediction. So these are the results of the 2 models, and for this particular case, we happen to have the DFT result as well, so that's also supplied over here. I show this particular case because this has actually been made. Right? This is a compound that has actually been synthesized and tested. Now, this is a simple enough case for density functional theory to handle without too much problem. But what if Greg comes to me and says, here is this gigantic monstrosity that we can make very easily in the lab. I need to know whether it's worth making or not. I have no idea what its band gap is going to be or the dielectric constant is going to be. Something like that. Of course, we can do the calculation using conventional methods, but it will take me a while to do it right. But the machine learning model can give us a prediction instantly. So for an experimentalist, here is a way of making a go, no-go decision, a quick estimate. This is not, we're not going to argue that these are accurate numbers, right? Errors of the order of 5, 6, 7%. But what he needs is a quick estimate, a practical answer. So that's example 2. Anatol, how am I doing on time?
Still have 10 minutes.
Okay. Yes.
Just a quick question. Basically, you assume that there is no dependence on morphology of the protein or polymer and all this.
Great question. There are 2 levels of morphology. One is a crystal structure, assuming it's a single crystal, right? There's no information in the machine learning model on the crystal structure. But more damaging, more important, is that there is no information on morphology, because polymers in reality are never single crystals, right? But that is true even with the DFT calculations. All of our DFT calculations assume single crystal. Right? Yes, you are absolutely right. These are the missing things. Okay.
The assumption is there's enough information in all your descriptors to capture that. Enough.
That's right. So one of the things we are working on is to come up with a new version of the fingerprint itself that will say something about longer range effects, right? Morphology. This is something we are working on at this time.
How much do you think it would help? You're already within 5%.
From DFT.
With respect to DFT, right? The thing is, in reality, since we are with DFT, we assume a single crystal environment. This is perfect packing. In reality, when you don't have a single crystal environment, you have free volume. Yeah, exactly. So those effects are not in even the DFT data set. Okay, last example. I'm going to go through this fast. Microscopic. So we talked about macroscopic, we talked about mesoscopic, and now let me talk about microscopic. Right? So here we shoot for accuracy. In the last 2 examples, we accept that the accuracy level is not going to be high, which is okay based on the applications. But there are other applications where we need to shoot for accuracy. So this is some recent work that we have been involved in, where we would like to predict the atomic force. Right? There are a couple of other groups that are also involved in the same direction. The rationale, the question is, given only the atomic configuration, can we directly predict the forces, the atomic forces, rapidly and accurately? The reason, of course, we are interested in this is because atoms respond to forces. So this capability can help accelerate molecular dynamic simulations. Right? So I want to show this paper, Richard Feynman's first paper, 1939 paper, Forces in Molecules, which is what led to the Hellman-Feynman theorem. Right? So let me just highlight a couple of things over here. Formulas have been developed to calculate the forces in a molecular system directly rather than indirectly through the agency of energy. Many problems molecular structure are concerned essentially with forces. The following method is one designed to obtain the forces at a given configuration when only the configuration is known. Right? So this essentially led to the Hellman-Feynman theorem, and so the concept is of course not new, right? So okay, so here is a summary of the concept that we are working on. So let's say you have an ensemble of atoms, and we are interested in finding the force on that particular atom, Fi. The potential energy is something we can compute, which is a global property of the entire system, and the force on a particular atom is of course related to the total potential energy, and that's the atomic force. Although it's related to the total potential energy, it's governed by what is happening locally around the atom. So our concept is, okay, well, if you have an atom over here and we want to find the force on this atom, we need to somehow capture the environment around that atom. How are the other atoms arranged around that reference atom? Right? How do we fingerprint that? Right? If we are able to fingerprint the environment around that atom, then we can establish a mapping between the fingerprint and the force on that particular atom. And once you do that, you have a force field. So that's the basic idea. So if you can map the fingerprint to the forces, then we have a force field. And for new cases, we can actually use that scheme. So here is the full scheme. It's kind of busy. It's got two panels: force field preparation or force field construction and force field use, right? Force field application. So we need to do a number of atomic reference calculations, density functional theory based calculations, let's say, where we use that to accumulate atomic configurations and forces, and then we take the atomic configurations and fingerprint it using this scheme. We have a fingerprinting scheme that is somewhat related to the symmetry functions of Baylor. And then we have fingerprints and forces. We break it up into training set and test set, and then we use our machine learning algorithm to come up with a predictive model of forces, atomic forces. Once you have a predictive model of forces, we can, when we encounter a new configuration during a simulation, we fingerprint it, use our predictive model, and get the forces, and we use that to go forward. Yes?
So I have a question on the fingerprinting. So
yeah.
These fingerprints are continuous in some sense?
They're continuous. Yes.
So do you, when you get fingerprints, do you have like a tolerance of if this is within like let's say 0.05 angstrom, then you call it the same fingerprint?
No, no, we don't do that. I don't fully understand your question, but no, I don't think we do that.
Okay.
Maybe we can get back to this question a little later. Okay. Okay, so if there are questions, I'm going to kind of go through this fast. If there are questions, we can come back to it on the details. So we have a force field for aluminum at this point. So there we subjected this force field to various tests, right? So here is an example of we considered a large unit cell of aluminum, 800 or so atoms that contain vacancies as well, and then we randomly perturb all the atoms. And then we wanted to know if our force field can be used for a simple geometry optimization exercise, right? So the force field can compute the forces on the atoms, and then you minimize the forces. Is it able to do a geometry optimization? So here is just a simulation of the geometry optimization process, right? So it seems to do it pretty good. Here is another example of diffusion. So here is an aluminum 111 surface, and there is an aluminum add atom on the surface. We wanted to model the diffusion, the long-range diffusion of that add atom, right? So that's the simulation over here using this force field, right? So the atoms are jiggling around, the add atom is moving around, so spanning a huge time scale in the simulation. But the real question is, yes?
I think, I mean, isn't this famous example where the atom should sink into the surface to do the exchange? Aluminum is famous because people were trying to compute the diffusion barrier with this process, and they could never match the experiment until they found out that the way it diffuses is that by exchanging with the surface.
Is it for the 111 surface?
I'm not 100% sure.
I do recall what you're saying, but I don't think it's the 111 surface, but I need to check. Yeah, 100. So okay, so the question though is whether, although we can do the simulation and watch this atom dance around, how accurately are the dynamics captured, right? Is this force field scheme capturing the dynamics, the physics underlying the dynamics correctly? Well, one way to do that is to do the simulation at various temperatures. And for each temperature, we calculate the average hop rate, right? And now if you plot the average hop rate versus 1 over temperature, you should get a Arrhenius behavior. And that slope of that Arrhenius behavior should be the activation barrier you can separately calculate. Okay? So, and we have done that. And for this particular case, we actually do get, so these are the, so that's the, this is the reciprocal temperature, rate constant of the average hop, and these points are the results of the simulation, and that's a fit. And these are the two, so of course from the slope we get the activation barrier according to the machine learning force field, and we separately calculate the activation barrier using 0 temperature DFT, nudge elastic band calculation, that's what we get. We have done the same thing for vacancy diffusion in bulk as well, and we get the same sort of trend. Yes, question? The error bar is because you see we cannot come up with one average rate. So the average hop time, we have a distribution of average hop time, right? So we have for each temperature there is a distribution of hop times, right? So that's why there is an error bar. So we just show the range of the uncertainty in the hop times.
Not the standard deviation, what is the range?
Sorry? Oh, it's asymmetrical because the log scale.
What is the range corresponding to? Is it your standard deviation?
Yes, standard deviation.
Sorry, Rampi.
Yes.
I think the question was why is it asymmetric?
The y-axis is the log scale.
Oh, I see.
Right.
So it is symmetric.
Yeah.
Can I get this is the question, I think, Noah. And so the error bar tells the different barriers which you have. It would not go away if you would do a longer time simulation.
It would not. Maybe it will.
In principle, you can, the reason why I'm doing it is really going out of the statistics, but
yes. Well, if you do for a very long time, then I guess you will tighten it up.
right?
Maybe there is a distribution. You will just tighten up the distribution. Yes, you are right. Right.
Which you could do with the fast.
We could do that. Yeah, sure. Okay. So now we subjected the force field for other tests, right? Further validation on situations not used during the training, not used during the construction of the force field, right? We considered 3 scenarios. Considered grain boundaries in aluminum, expanded and compressed situations in aluminum, and an edge dislocation, right? And when we do this, we also wanted to compare how the force field is performing with respect to DFT, but also how it is performing with respect to a very well understood, very well accepted force field for aluminum, which is the embedded atom method, right? So machine learning force versus the DFT force for grain boundaries. Our force field, which we call AGNI, by the way, it's all red. And then the interatomic potential based on embedded atom method is very competing. There's not much difference between the two. Here is the corresponding plot for expanded and compressed situations. Once again, both the methods are almost equivalent to density functional theory, but when you go to the edge, so we created an edge dislocation in aluminum, rather large calculation, perturbed the atoms around the dislocation core and everywhere, computed the forces using DFT, computed the forces using machine learning, and that's the red plot. Okay. As you go to larger and larger forces on plus or minus, there is some deviation, but it's somewhat small, right, relatively. But if you look at EAM, which is the blue stuff, it fails. Right? So embedded atom method and many classical force fields are built from equilibrium sort of situations. And so if you go stray far away from equilibrium, they are prone to fail. And I think DeVita's group has recently, okay, all right, has recently also come up with the same sort of conclusion based on comparison between embedded atom method and DFT for dislocations as well. So that's kind of what we are seeing over here. Can I finish and then we'll come back to your question, because the chair is asking me to shut down. Okay. Okay. One last slide. Energy. So since our force field can predict energies, can we get forces? Since our force field can predict forces, can we get energies out of that? Sure we can. By integrating the forces along the trajectory, we can actually get energies. And this is a plot that shows energy predictions from our force field as a function of time for aluminum at various temperatures. These are big aluminum supercells performed at various temperatures, and these blocks that you see are the corresponding DFT calculations, and our forces, the energies that we get from force integrations are pretty good. This is the corresponding thing for EAM. I'm going to rush through because I'm really out of time. Okay, so really fast, we looked at three different classes of fingerprints: macroscopic, mesoscopic, microscopic. There is a lot of other work which I did not have the opportunity to touch on. But in each of these classes, there is plenty of vigorous activity going on right now. Although there's a lot here, perhaps in this bottom category. So critical next steps. I'm going to finish with this slide. Decision on whether to use machine learning. That's actually a very important step. This is a very hot and very exciting time for people in material science getting into machine learning. But I get approached by many people to collaborate to do machine learning. So I ask them, is that the right tool for the problem that they have in mind, right? So that's an important thing. Choice of fingerprints. Uncertainty, out of domain quantification. How do we know that our statistical or machine learning model is being used in the correct domain, right? How do we quantify the uncertainty of these predictions? And if we know the uncertainty, if we're able to properly quantify the uncertainty, and if we're able to estimate whether we're going out of domain, we can actually make it adaptive. We can now reparameterize our machine learning model based on the new situations that have been encountered and make our model better. Machine learning should not be a one-shot deal, right? We want to keep doing it again and again to improve it continuously. And finally, we want to show the value to people outside of our community, right? We want to make it useful and practical for the application domain people. Right? So with that, I'm going to close. Let me thank the people who actually did the work. The initial part of the stuff that I presented today was done by Ghanshyam Pilania, Chen Wang, and Venkatesh Botu, who all moved on. And currently, a number of other people in the group are actively involved in it. And James Chapman is sitting over there. He's attending this workshop, thanks to the organizers. And the work that I presented today, almost in its entirety, was largely heavily funded by the Office of Naval Research. With that, I'm going to close. Thank you all for your attention. I'm just going to put this quote up there.